Let us begin. Yeah, so this is the diagram that we are going to investigate today. So the interval 0, 1 is clearly an interval in real numbers, correct? So this inclusion is clear. Then from real numbers we will give a map using Dedekind cuts to power set of rational numbers. But what is power set? We saw it in the last lecture. It's same as, it is in bijection with functions from Q to 2 via characteristic functions of subsets. So this is same as, because we have seen that if A is equinumerous with C and B is equinumerous with D, then functions from A to B is equinumerous with functions from C to D. Yes, so this part also we have done, and over here from fun n2 to 0, 1 will give the Cantor's middle third set argument. Yes. Okay, so this map is, if you are given any subset y, where will y go here? It will go to the characteristic function of y, and which is a function from rational numbers to 2. How is that function defined? It will send a rational number, let us say x, to 1 if x belongs to capital Y and 0 otherwise. And in the reverse direction, what you do, you are given some function from Q to 2. This function we will map it to f inverse of 1. Please verify that this is a bijection. Yeah. So our job today is to finish these two green descriptions. So real numbers are thought of, real numbers are complicated actually, yeah. Even though all of you feel like you know real line, but real numbers are complicated, and they were actually introduced to fill up gaps between rational numbers. All of you know that rational numbers are dense. Given any two different rational numbers, there must exist a rational number between them, correct? So let us write down that property first. Yeah, dense rational numbers. Rationals are dense linear orders. Okay, so let us quickly recall what linear order means. Here I am talking about rationals with less than relationship. So first thing is that, what are the properties of this strictly less than relationship? Can an element be related to itself? No. So negation of x less than x. Yeah, I can write down, if you want, I can write down more formally. For all x, negation x less than x. This is the first property. What is the second property? Transitivity holds. If x is less than y and y is less than z, then x is less than z. So for all x, y, z, x is less than y and y is less than z, then this implies that x is less than z. Okay, so this first property is called irreflexivity. Yeah, this is exactly the opposite of reflexivity. Reflexivity says that two elements are always, like one element is always related to itself. Irreflexivity says that one element is never related to itself. Second property is transitivity, all of you know this. And third property is that for all x and y, if x is not equal to y, yeah, negation x equal to y, then this will imply that either x is less than y or y is less than x. All of you agree with this? Two numbers are always comparable. If they are distinct, then they are comparable. So actually there are three possibilities. First possibility is that two numbers are equal. Second possibility is that x is less than y, and third possibility is y is less than x, and therefore there is the right name, it's called trichotomy. Okay, trichotomy means three possibilities. It has to be one of the three possibilities. And finally we have this density property. I'm just going to write it here. For all xy, if x is less than y, then this implies that there exists z such that z is less than y and x is less than z. What I am saying is that given any two real numbers, any two rational numbers, if this is x and y, then there must exist a rational number between them. Can you tell me how to find such z? Average, very good. So this is called the density property. So therefore rationals are dense linear orders. Linear orders are things which satisfy first three conditions. Okay, 1, 2 and 3, and it's moreover a strict linear order, right? Strict. I'm not writing less equal, I'm writing strictly less than. So first any set equipped with a binary relation, this is a binary relation, less than is a subset of q cross q, which satisfies first three properties, is known as a strict linear order. And if it satisfies all four properties, then it is a strict dense linear order. Okay, so density is going to play a very important role. So we want to talk about real numbers. So real numbers are actually completions of rational numbers. Completions in the sense that they will fill up gaps. Well, for example, give me an example of a real number that is not rational. Root 2. Okay. Can somebody tell me some decimal values for root 2? 1.414. Okay, this is the first answer where everybody tried to speak. You all like numbers. Yeah. Okay, 1.414. So actually if I take a sequence 1, 1.4, 1.41, 1.414 and then continue like that, it is a sequence of rational numbers. Does it converge? Yes or no? No? I mean, yes, exactly, that's the question. Yeah, where? Converge where? Does it converge in rationals? No. But does it converge in reals? Yes. Yes, it will converge to root 2. So actually root 2 is supposed to be there. Yeah, it's a gap which is meant to be filled in. Correct? So actually whatever sequence we are talking about, that doesn't have to be the only sequence. We can have multiple sequences. But instead of that, what if I define this f from real numbers to power set of rational numbers as this. So send a real number to all those rational numbers such that they are less than that real number. Okay, so if we are talking about root 2, then we will map it to all the rational numbers which are smaller than that. I mean, you can take an increasing, monotone increasing sequence in that which converges to real number r. So actually this gives us a partition, right? So this gives us a partition. So f of r disjoint union q minus f of r, right? Q minus f of r, you understand? it is, I will write it down. So, this is equal to rational numbers, correct. So, this is known as a Dedekind cut. In rationals. I am actually being a little bit sloppy here. Yeah, this is not all of them are actually Dedekind cuts, but for the purpose of this lecture, let's do this. So, can you describe this set, all those rationals such that what happens?
Q greater than equal to R.
Yes, Q greater equal R. So, actually technically Dedekind cut is when Q in Q such that Q bigger than R and Q in Q such that Q is smaller than R, yeah, they will form a partition of rationals. Yeah, that's a perfect Dedekind cut. Yeah, but right now I just want to be a bit sloppy. So, this f function, what can you say about f? It's mapping a real number to an interval in rationals. What can you say about f? What properties of functions do we study? Injectivity, surjectivity. Is this injective? Yes. So, f is injective. How do we show that? Suppose R1 is not equal to R2. Well, real numbers are also dense linear orders. So, if R1 is not equal to R2, then either R1 is smaller than R2 or R1 is bigger than R2. Yeah, so without loss of generality, assume R1 is smaller than R2. Okay, now we have to use a stronger property, that rationals are dense in real numbers. Rationals are dense in real numbers. How do you prove that? Since rationals are dense, this you must have done in your first calculus lecture. Rationals are dense in reals. There is some Q0 in rationals such that R1 is less than Q0 is less than R2. Anybody who can tell me why rationals are dense in reals? Given two real numbers, does there exist a rational number between them? Yes. So, how do you find such a rational number? Do you remember something called the Archimedean property? Okay, so use that to get this. So now note that Q0 belongs to f of R2, but Q0 does not belong to f of R1, because f of R1 is the collection of all rationals which are less than R1. Well, Q0 is bigger than R1, so it is not, and Q0 is less than R2, so it belongs to f of R2, and therefore f of R1 is not equal to f of R2. We started with R1 not equal to R2, we obtained f of R1 not equal to f of R2, which means f is injective. So, via this construction we have finished the description of this injective map from DL numbers to the power set of rationals. Understood? right? Archimedean property, you have to figure it out yourself. Okay, so now let's complete the circle. So we are at functions from natural numbers to 2. So functions from natural numbers to 2 are what? For 0, I assign one element, either 0 or 1. For 1, I assign 0 or 1. So it is nothing but a sequence of zeros and ones. Yeah, functions from n to 2 are sequences of zeros and ones. Okay, let me write that down. If f belongs to functions from n to 2, then f is a sequence, is a binary sequence. Actually, we can work with binary sequences. So all of you know that every number has a binary expansion as well. Similar to decimal expansion, every number has a binary expansion. But there is a problem. Yeah, if you remember, while constructing real numbers with decimal expansions, we ran into some issue, right? 0.99999. That is same thing as 1.000. So those two numbers have to be identified. Any sequence, any decimal expansion that ends in a sequence of 9s has to be taken back. Yeah, I mean you can truncate it and add 1 to the previous number, correct? So now even if we deal with just binary sequences, we are going to run into the same problem. So for example, 0.11111 is same as 1.00000. So that's a problem. So we are going to remedy this by not using binary expansions, but by using ternary expansions instead. Yeah, binary and ternary. So I am just going to write certain things down. We don't use binary expansions since let's say 0.1 dot is same as 0.1 in binary. Maybe I should write this binary. So we don't want to run into these problems. So our remedy is we will use ternary expansions instead. So what are ternary expansions? What digits can we use?
0, 1, 2.
0, 1, 2. Which do not include 1. Okay, so in ternary expansion also, let me write it. So in ternary expansion, what will happen to 0.02 dot? 0.1000. However, because we are blocking the use of 1, now we have an advantage. We don't have to make a choice. We are forced to use only this expansion and not that one. Yeah, imagine any situation where we can only use zeros and twos. If there is a string ending at 2s, then the previous digit cannot be 2. Yeah, we have chosen the maximal string ending at 2s. So the previous digit has to be 0. So therefore, when you round it up, that 0 has to become 1, but 1 is not allowed. Okay, so we are being clever here. Yeah, we don't want to run into any problems, and in this way actually whatever numbers we can write down which have ternary expansions which avoid 1, that will be a one-to-one correspondence. Okay, so the real numbers which have ternary expansions which do not include 1, well, they will have only one ternary such expansion. Okay, I will repeat it and write it down.
So whenever the 1 will come, we will replace it by this 2.
No. See, that's not correct. Whenever 1 shows up, there can be at most 1. See, we are not allowing something like 0.101010. Yeah, that will run into problems. We are not allowed to use 1. I'm just saying whenever your string ends at, whenever your ternary expansion ends in a string of 2's, then you cannot round it up. Yeah, the rounding up effect is gone because then you have to replace that previous 0 by 1, and which we don't want. Okay, so the real numbers which admit ternary expansions avoiding 1 have unique such expansion. Okay, let us start with something. I am only going to work with all the ternary expansions. So let us only work with ternary expansions of the form (0.a0 a1 ... where an belongs to 0 or 2 for n in omega. Okay, so what I am fixing is that there is no integer part here. Yeah, the integer is 0, so we will always land between 0 and 1. Okay, so let us do some examples. Does 0 have a ternary expansion that avoids 0? What will be the ternary expansion of 0? 0.000. Yeah, so definitely 0 is equal to 0.0 dot. Okay, well done. Can 1 have a ternary expansion that avoids 1?
0.2.
Yes, very good. 1 is equal to 0.2 and dot. I mean, I should write this 3 at the bottom. Can half have a ternary expansion which doesn't include 1? No. 0.5. 5 is not allowed ternary expansion.
0.02222.
0.0?
2 dot.
0222 dot. Yeah?
Yeah.
What is this number? Please use geometric series to conclude that this is actually 1 by 3. And the immediate next number than this is actually 0.2 in ternary, which happens to be 2 by 3. Okay, so now this is telling us something, that 3 is important, and we are going to construct this Cantor's middle third set. Okay, so start with, so this is a recursive definition. So start with A0 equal to the interval 0 comma 1. And what is my rule? That whenever I see an interval, I will cut out its middle 1/3 open part. So for example, this is my 0, 1, okay. Then in the next step, I am supposed to cut out this middle 1/3 part. So this will be my 1/3, this will be my 2/3, and I am supposed to cut out this open middle part. So what will be my A1? A1 will be 0 to 1/3 union 2/3 to 1. Okay, so now let me draw it again. The middle part is not there, but once again I see an interval, in fact two intervals, 0 to 1/3, 2/3 to 1, there are two intervals, and I should cut out the middle portions of each one of them. So I should take this, and I should cut out this part, this and this, I should cut out this part, and this will be, what is this number? 1/9, this number is
2/9,
2/9, this is 7/9, and this is 8/9, and I continue this process, yeah, continue using recursion, and then the Cantor set C is defined to be intersection of all ANs. This is the Cantor's middle third set. Middle third is the name which is given because we are cutting out middle third. Yeah, you can define different types of Cantor sets. It doesn't have to be this. This is actually quite an interesting set. Yeah, of course, who discovered this? Cantor. Yeah, I'm saying that name so many times. So this is very interesting. It contains 0, it contains 1. Yeah, however I cut down things, yeah, it will always contain the endpoints of the intervals. Correct? So it will contain 0, 1/9, 2/9, 1/3, all these 8 points. It will contain even more. Yeah, at every time you are creating some endpoints. So those endpoints will always be there. Well, let us figure out how much length we are cutting down. So how much length? Are we cutting down? At the first step, going from A0 to A1, how much length are we cutting down?
1/3.
1/3. At the next step, how much length?
2/9.
Okay, so 2/3 square. At the next step,
2 square by 3 cube.
right? 2 square.
By 3 cube. 3 cube.
Okay. And please do the sum.
1.
All of you know how to do series. Make sure this sequence is correct and it should turn out to be 1. So look at what's happening. Yeah, we started with an interval of length 1 and we are cutting down length 1. So therefore what remains is also known as Cantor's dust. I mean, essentially nothing is remaining, right? It's like dust. However, we are going to show that it is uncountable. It's not countable dust, it's uncountable dust. Okay, so now I am ready to say what I want to say. Please look at this. Yeah, every such number every number in the Cantor's middle third set has a binary expansion which does not include 1. As a ternary expansion that does not include 1. So I am just going to write it down that every R in C has a ternary expansion avoiding 1. And now I should be able to give you a function. So I start with the function f. Yeah, look here. F is a function from natural numbers to 2. I will give you a function.
Sir?
Yes?
But C is just a set of 0 and 1.
C is not a set of 0 and 1. C is the zeros and ones. What do you mean?
Like we have cut down the whole length.
No, we did not. See, the 1 by 3 will always be there in this set. It will contain 0. Yeah, no matter which middle third you cut out, which open middle third, 0 will continue to be there. 1 will continue to be there. 1 by 3 will be there. 2 by 3 will be there. 2 by 9, 1 by 9. All of those points will continue to be there.
There won't be any interval, there will be discrete points.
Exactly. That's why I am calling it a dust. There won't be any interval. Yeah, once you learn measure theory, you will see that this is a measure 0 set. But there are uncountably many points. So every R in C has a ternary expansion that avoids 1. And moreover, if R belongs to 0, 1 and has a ternary expansion avoiding 1, then R belongs to C. So Cantor's middle third set is precisely the set of all real numbers in interval 0, 1 which have a ternary expansion avoiding 1. And what did we write on the previous slide? That the reals which admit ternary expansions avoiding 1 have unique such expansion. Okay, so let me finish by saying, so now define a G. Okay, this G is going from functions from n to 2, which means it is a sequence. Yeah, sequence of zeros and ones to real numbers, where I send a function f to f of n divided by 3 to the power n plus 1, multiply this by 2 and then take the sum over all n in omega. Okay, let's take a pause and understand what this is saying. This is a sequence of zeros and ones. So if it is 0, then 2 times that will continue to be 0. If it is 1, then twice it will be 2. So I am simply writing down a sequence of zeros and 2's, and those are the weights, and I am adding powers of 3. So this is precisely a point in the Cantor's middle third set. Yeah, so that image of G is precisely C. Okay, every function, so let me maybe give an example. Yeah, for example, my f is if f is the sequence 0, 1 and 0, 0, 0. Okay, this is my sequence. What will I map it to? Then G of f will be This is my 0th location, this is my first location, third location, and so on. So what will this point be g of f? Yes, 2 by 9. Right, 2 by 9 is a point. I hopefully convinced you 2 by 9 is a point in the Cantor set. So every such f will be mapped to a point in the Cantor set. Right? So this is precisely the image, and clearly every such point, yeah, I mean by this statement, so by star, okay, this is my star, by star G is injective. So therefore Cantor dust is an uncountable dust. Yeah, it's a major zero set. It doesn't have any length inside it. Understood? This because we are writing down, I mean, see, this is precisely the ternary expansion which cannot use 0 and 1. We are multiplying, we are starting with a binary sequence, and we multiplying binary digits with 2 will give you only zeros and 2s. So therefore this is precisely the ternary expansion. Yeah, so how do you obtain ternary expansion of a number? If you are given number half, how do you obtain its ternary expansion?
Divide by 3 and take the limit.
Divide or multiply?
Number 2 expansion.
If I start with half, real number half, then I multiply by 3, then I collect the integer part of that. Then again whatever is the remainder I multiply it by 3, again I collect the integer part. Yeah, that's how the process should go. And conversely, given any such expansion, you can simply take this series, you can show this series is convergent, right? It's dominated by a geometric series, so therefore it's convergent. So do that. So in the reverse direction, from any such expansion you get a real number. Okay, so this is actually a perfect bijection, and moreover we are avoiding our usual glaring problem with expansions, that series ending in the maximal digit, yeah, the string ending in maximal digit, in this case 2, will always round up to the previous number, like one added to the previous number. We don't have that problem here because we are dealing with only zeros and 2s. So that's how smartly we have avoided talking about things which could cause problems. Hopefully this is clear. Yes? Huh? 2 by 9. Just add. This is first location. So this is 2 times 1 divided by 3 to the power 1 plus 1, which is 9. So 2 by 9, and all other numbers are 0. Okay.